I'd like to welcome everybody to our Weizmann Space program today, and I'd like to especially give a big shout out to Andy Weizmann, who has head the Bay Area Weizmann programming. So thank you very much. For those of you who don't know, the Israeli Action Committee of Emanu-El is now in our 8th year. We try and bring 7 to 8 programs a year. Those of you who are members, we'd love you to join. We try and highlight and foster a love of Israel, whether it be economic, political, social, or cultural events. We do everything from have debates between right and left on the settlements to have Israeli wines to Israeli space programs such as this. Just a few weeks ago, we had a big program on helping the remaining 14,000 Ethiopian Jews that are stranded in Ethiopia under civil war, raise some funds for food until they're able to come to Israel. There's some great pictures and great links to that on our webpage if you haven't watched it yet. So I would encourage you to do so or talk to Ariana if there's any issues there. And I thank those of you who donated. And so without further ado, I'm going to introduce Andy to run and moderate this program and thank him very much, as well as thank Ariana Stoke and Jonathan Singer for making this whole thing possible. There's so few Reform synagogues that have embraced Israel. And I feel like Rabbi Singer should get a huge shout out and support for all that he's done in fostering a love of Zion.
Thanks, Jordan. As Jordan said, I'm Andy Weizmann. I'm a community member at Emanu-El and a member of the Israel Action Committee and executive director of the Western region for the Weizmann Institute of Science. As such, I'm delighted to welcome our guest speakers today, Roei Elzari, quantum physicist and vice president of development and communications at the Weizmann Institute of Science, and Avishai Gal-Yam, head of the Department of Physics core facility and avid stargazer. A little bit about Roei. Roei was born in Israel and received his Bachelor of Science in Physics from the Hebrew University of Jerusalem. He received his master's and PhD from the Weizmann Institute of Science and conducted his postdoctoral research at the National Institute of Standards and Technology in Boulder, Colorado, in a group of David Wineland, a 2012 Nobel laureate, and where at least one of his children, I think, was born. He joined the Weizmann faculty in 2007 and was appointed Vice President of Development and Communications in 2019. A little bit about Roei's research. He conducts research in the field of ultra-cold atoms. One of his research efforts is quantum computing, the development of computing systems that make use of the principles of quantum mechanics. Such systems have the potential to perform immense information processing tasks that are out of the reach of today's regular computers. If such systems are indeed built, they will revolutionize the world of computing, providing an entirely new approach to ensuring the secrecy of information such as online banking transactions, among many others. Roei, thanks for being with us today and for help validating the point and one of the main principles of quantum physics, that you can indeed be in two places at once. Before we begin our discussion of Weizmann and the Israeli space exploration, Roei, perhaps you can give us a brief overview of the Weizmann Institute, where it is, and what makes it so unique in Israel and the world of science.
Hi, Andy. Thank you very much for the kind introduction, and thanks everyone for tuning in. I just like to mention that Avishai Gal-Yam will speak after me. Has recently been nominated to be the Dean of Physics at the Weizmann Institute. So he's our physics boss, if you like. So yeah, gladly I'll give a short overview of the Weizmann Institute of Science for those of you who are not familiar. We're on the global scale, we're a relatively small research institute, 250 research groups, located a little bit south of Tel Aviv, in the city of Rehovot. Weizmann Institute was founded by the first president of the state of Israel, Dr. Chaim Weizmann. Actually, Chaim Weizmann, who was a professor of chemistry at the University of Manchester and a statesman and one of the probably most important Zionists at the turn of the 20th century, when he lost the elections for the head of the Zionist movement, he decided to go back to research and found a small research institution. At that time, that was a chemistry lab. And what Chaim Weizmann had in mind and his vision was that he believed that scientific research would form the basis for the economy and driving force for the society, for the future state of Israel. And he viewed science as a very important tool to advance not just the state of Israel, but the entire region of the Middle East. And he viewed science as a bridge between Jews in the Middle East and other nations in the Middle East. And I think that today, when we look, almost 90 years after the fact, we can appreciate this vision because, back in those days, many of the Zionist leaders viewed the future of Israel in agriculture, which is, of course, very important. I myself grew up in a moshav, but if you look at the economy of Israel today, and if you look at the strategic assets of Israel today, they, to a much larger extent, rely on our ability to produce technology and produce knowledge, and this is exactly what science is about. From a small chemistry lab in 1934, Weizmann Institute, actually through the help of Chaim Weizmann's American friends, who Andy is an important member of this committee today, through the help of the American Committee for Weizmann, this small chemistry lab grew into a research institute in 1949, which actually performs research in all of the exact and natural and life sciences. Today, Weizmann Institute is home of roughly 270 research groups, again, performing research all the way from math, computer science, chemistry, physics, sustainability and environment, through life sciences, biology, medical research. I think that if you look at the history of Israel and the history of Weizmann Institute, they're strongly intertwined. The first digital computer that was built in Israel was built in the 1950s, the WITESAC at the Weizmann Institute of Science by one of von Neumann's students, who was part of building the first computer in the US as well. And that was, mind you, 1950s, very early on in the days of computer science, the first particle accelerator. Several of the blockbuster drugs, in fact, Teva, which is the largest pharmaceutical company in Israel, has built itself on Weizmann Institute IP. So I think that the strength of Israel has been going hand in hand with the advancement of research at the Weizmann Institute of Science. And I think we grew to a place where today, and you'll hear a lot about it from Avishai in a few minutes, we're really at the point where we can be as ambitious as launching a space telescope to space. And for those of you who know a little bit about space programs, this is by no means an easy feat. That's a huge technological and scientific project. If I have the floor, I might as well use it to show off a little bit. So I'll say that Weizmann Institute scientists attracted 3 Turing Awards, which are the highest awards in computer science. 3 Nobel Prizes in chemistry were awarded on research that was done at the Weizmann Institute of Science. One of these laureates, Ada Yonat, is still at the Weizmann Institute. She received her Nobel Prize for discovering the structure of the ribosome. This is the protein factory in every cell, and a very important ingredient in the machinery that viruses hijack and use, but also in our understanding of how to stop these viruses, if I'd like to be contemporary and relevant to the situation around us. I'll end by mentioning maybe 3 facts that I think make Weizmann Institute a unique place in my mind. One is that the research at the Weizmann Institute of Science is really not based on any scientific agenda. It's what we refer to as curiosity-driven research. We don't have any applied faculties. We don't have an engineering school. We don't have a medical school. The motivation behind research at the Weizmann Institute of Science is basic research and it's driven by the curiosity of the researcher, not by goals that management or government would put in front of researchers. And we do that because we believe that nobody at the Weizmann Institute of Management or the Israeli government or the US government, nobody can actually foresee the next scientific breakthrough. The next scientific breakthrough always happens bottom up. It always happens by scientists asking questions of, gee, I wonder why that works the way it does, and what's the mechanism behind this. It's not coming out of the desire to generate a new technology, but rather by the desire to understand how nature works. The other, I think, point that makes Weizmann Institute unique is that, again, as I said, we don't have any scientific agenda, and therefore we never recruit people by their scientific expertise. So we don't believe in scientific agendas. All we believe in is in people. What we try to do is find the best people, attract the best people, and hire the best people, the most creative and talented people, and then put in their hands all the means that they need in order to carry out their research. And we believe that the next scientific revolution, the biggest discoveries, would always be found this way. And the third fact that I wanted to highlight is that the Weizmann Institute is a very flat place, meaning it's not very hierarchical. People can speak with each other. There aren't any walls between faculties, graduate students, and we're a graduate school. We're not a university. Graduate students can be admitted into one teaching program, let's say in physics, then do their research anywhere on campus, biology, chemistry, anywhere else, and vice versa. What we're trying to create is a very interdisciplinary community of scientists. And one way to support that, in fact, comes from the fact, and as both Avishai and I can attest, about 2/3 of faculty live on campus, and that's why the Weizmann Institute is not just a research institute. In many ways, it's also a kibbutz. People know each other. Our kids play together in the playgrounds. We have kindergartens on campus, and I think that this sense of community and this very direct communication does not also support a good lifestyle, and it doesn't only strike balance in the way people combine their work and their beyond work life, but it also encourages discussion, it encourages collaboration, and I think that this is another driving engine behind the success of the Weizmann Institute.
Thanks, Rory, for encapsulating about 90 years of history into a short talk. It's an endlessly fascinating place, and that's why I choose to be affiliated with it. So I'd like to switch topics for a second before we launch into our discussion of the Weizmann Space Program. At our last Israel Action Committee gathering, we learned about and discussed the plight of the 14,000 or so Ethiopian Jews who remain in Ethiopia and await Aliyah to Israel. Thanks to our committee chair and other generous members, we've raised almost $125,000 to date since last month to support the Ethiopian community. And we're still accepting donations for that. So I thought it would be helpful to tell the audience about how Ethiopian Jewish immigrants are welcome to Israel, specifically Weizmann's Sparks of Science program, which supports Ethiopian Israeli high school students. So what's the program and how does it impact the lives of these students and the families?
So to put the Sparks program is a fascinating program, but to put it in context, in 1999, the Weizmann decided to establish an arm for education and outreach. In fact, Weizmann Institute has been engaged in outreach and education. We believe that it's our job not just to explore science, but also to teach kids and the rest of the population about scientific findings, establish scientific literacy, and we view this really as part of our mission. In 1999, we established the Davidson Institute of Scientific Education, which is the education and outreach arm of the Weizmann Institute of Science. Davidson Institute is a home for about almost 70 different educational programs for kids in all ages, both online digital as well as physical and on-premise, on campus at the Davidson Institute, which is on the Weizmann Institute campus. And these programs are really very heterogeneous, not just in their scientific content, but also in terms of the target audience. And sometimes you build programs that are directed towards excellent students, to support excellence, sometimes to take weaker students and advance them, sometimes towards weak socio-economical parts of the Israeli society and outside Israel. Spark's program is actually both directed towards excellence as well as towards a part of the Israeli society which traditionally has been socioeconomically weak. So it's targeted towards the Ethiopian community in Israel. The program started at the Ethiopian community in Rehovot, which is rather large, but since then expanded to all the Ethiopian community in Israel. It takes excellent kids, so kids with orientation towards the sciences, and gives them, from the Ethiopian community, gives them extracurricular activities, both digital, online, as well as visits on campus, visits in labs. And this program is also combined, so besides the scientific aspects of it, it also combines social activities and social meetings and also activity within the community. So I think this program takes kids who have talent in science and can really accelerate them. Some of the graduates of this program made it into technological units in the IDF. We have some of the graduates of this program already students at universities in Israel. So we believe this program is really important and strong.
Yeah, it's I met some of the students there. And one of the things I was really struck with was their English proficiency. They almost speak like native speakers, which I know in Israel is a very, very strong thing. So right now we're going to say goodbye to Roe. He just got back from some international travel. Thank you, and enjoy the rest of your evening.
Thank you very much, guys.
So before I introduce our next guest, I thought it would be valuable to show you a brief video about Weizmann's UltraSAT satellite, which features a few of the scientists involved in the project, and they can get into more specifics. Alex, can you play that video for us now?
Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Liftoff.
Did you ever wonder what we're made of? We're all stardust. The elements that compose us are actually forged in huge cosmic explosions in outer space. In understanding these cosmic explosions, you have to actually look at them at the very second they ignite. And that's something you can't do with ground-based telescopes. If you want to do that, you have to take your telescopes, put them on satellites, and launch them into outer space. And that's exactly what we're going to do.
UltraSAT became a project way back in 2019, but the truth is that we've started thinking about it already in 2010, trying to find ways to answer some of the big questions in astrophysics using Israeli technology.
The main motivations of UltraSAT are transient astronomy. Transient events are rare events. You can't just wait and on a very small region in the sky and hope that you will have that event happening there. So you need to monitor a large fraction of the sky, so the probability of having those transient events are large.
For UltraSAT, this was probably one of the biggest challenges, to find an optical design that is capable of providing both the very wide field of view and reasonable image quality.
There are signatures that you can see in the UV light curves that you cannot see in other wavebands, but you must go to space in order to observe in the UV, because UV is not penetrating in the atmosphere.
Specifically, it tells us something about very hot objects in the universe of temperatures above tens of thousands of Kelvin, which is usually the setup in cosmic explosions like supernovae.
By studying these objects, we hope to answer some of the big open questions in astrophysics and in physics in general, like how black holes grow and affect their environment, how stars explode, where in the universe the heavy elements were produced, and which stars are most likely to host habitable planets.
You look at a phenomenon and you say, according to all my theoretical understanding and my previous experience, this thing should not exist. And yet, it exists. And that's what really drives our knowledge forward. Finding the thing that you didn't expect, that you didn't predict, and you cannot explain, at least initially. Because we are taking data that nobody's taken before. Nobody's looked at such images. Nobody has these big UV cameras in space. You just cannot take this data any other way.
One of the unique aspects of UltraSAT is that it is the first major project in which the industry and the academy are collaborating so closely and on such a large scale. The things that UltraSAT accomplished was to strengthen Israel's international standing. NASA has chosen to join UltraSAT under Israeli leadership to provide the launch for this mission.
There are very few institutes in the world who have a space research program. This puts us at this very unique and exclusive category that would be a game changer. So we would like to invite you to join us on this really frontier-breaking journey together with us.
So today we get to hear from one of the pioneering scientists behind Weizmann's Frontiers of the Universe initiative, Professor Avishai Gal-Yam. Professor Gal-Yam is a cosmic detective who seeks to identify the stars that explode in supernovas. These stars can give us vital clues about the origins of the elements and our universe. Avishai earned his bachelor's and doctorate from Tel Aviv University. He then received NASA's prestigious Hubble postdoctoral fellowship and spent 4 years here in California at Caltech. He joined the Weizmann Institute in 2007, where he's a member of the Department of Physics and Astrophysics, and now apparently the dean. Congratulations on that. We are really fortunate to have Weizmann's very own supernova hunter here with us today. Oh, and by the way, if you have any questions for Avishai or anything that Roe mentioned before, please put those into the chat, and right after our discussion, we'll get to them at the end of this presentation. So Avishai, welcome. Thanks for being with us.
My pleasure.
We just saw a little bit about UltraSAT in that video. And I know that UltraSAT is an important part of a larger astro and particle physics initiative at Weizmann called Frontiers of the Universe. Can you tell us a little bit about Frontiers of the Universe before we talk about UltraSAT specifically?
Yes, certainly. So in recent years, we realized that we live in a unique time in physics and in science in general, but particularly in physics, where there have been technological advances and also advances in our knowledge and theory that allow us to understand unique things about the universe from combining two types of physics. One is astrophysics that studies the distant universe, and you saw, stars exploding halfway across the visible universe. But you gain a lot of insight with combining astrophysics with particle physics that actually studies the smallest scales you can imagine of matter. These are subatomic particles, the most fundamental building blocks of the universe. And this has been a topic of intense research on the ground with particle accelerators, huge ones, very expensive ones. And it turns out that combining the advantages of space, which gives us this huge laboratory where you have infinite energies, not infinite, but very large, that you cannot fortunately create on Earth, and very large distances and velocities and high energy densities, allows you to study particles in a way that you cannot do on Earth. And on the other hand, studying particles allows you to understand astrophysical phenomena much better. And the Frontiers of the Universe goal is this big initiative here at Weizmann to bring these two areas of physics to be closely tied together at Weizmann. So we're bringing together all the relevant scientists into the same environment and funding programs that would foster very intense collaboration, theoretical, experimental, instrumental between those two communities. And as you saw, this also requires, and our management has understood this and supported this, this requires substantial support of research, because this is big science in physics. It's not something a single, however talented individual scientist can do in a small lab. You need big facilities, you need to go to space, you need to access the largest accelerators, you need to build new technologies. So the Frontiers puts the resources to support all of these things together.
Great. So now let's dig down a little bit more deeply and specifically. So tell us about UltraSAT, including its partners, when we can expect its launch, and its scientific purpose and what we hope to uncover and discover through its launch.
Right. So let's start talking about UltraSAT, which is a space mission, an Israeli space mission. So first of all, let me try to lead you, to make you imagine the mission, right? So the core of the mission is a telescope, which you can use to see very far away. And this telescope is about as big as, let's say, myself, more or less. So it's about 170 centimeters, let's call it 6 feet tall, about, 2 feet on the side. Okay, I'm not 2 feet on the side, but unfortunately,
Not yet.
But more or less like that. And this telescope sits inside a spacecraft, which is not much larger than the telescope itself. It's very compact, and it's very effective in supporting the science. And this is going to be launched to space. Now, what's so special about this telescope? The telescope has a camera with sensors that can see very large fields of view, so cover big parts of the sky, and are sensitive to UV photons, ultraviolet. So ultraviolet radiation does not penetrate the atmosphere, at least the type of ultraviolet we are interested in. It's not the tiny bit that does penetrate and make our skin a little bit darker. But the far UV that we are interested in does not penetrate, fortunately again for us, does not penetrate the atmosphere. In order to observe it, you have to go to space. And UltraSAT is unique in the sense that the field of view of the telescope is so large that you can just stare at a big piece of sky at the same time. And you know that something interesting is going to happen there. And you can imagine that by thinking about two types of things, right? Imagine you have a very narrow telescope that gives you a very, very fine image, but it only covers a small spot on the sky. And one such telescope, by the way, is the very famous Hubble Space Telescope that NASA launched to space more than 20 years ago. So this is a very good instrument if you know what it is that you want to observe, because you have to point it there and then you can study it very well. But if you don't know what you want to study, there's no chance that this unknown thing will just happen where you are looking at space. So our telescope has a much wider field of view. So it covers a few percent of the entire sky in a single image. And so if we don't know where something is going to happen, but it happens, stars explode all through the universe, so they just pop off in different places in the sky. By just looking at a single place, we know that every day something is going to happen within our field of view. And then once we locate it, by the way, you can also turn to this point, which is now known, other instruments, like the Hubble Space Telescope and many other telescopes. So it's not only to study these interesting things, it also allows other instruments and other scientists to study them. So it's a special telescope with a special camera that sits inside spacecraft. And it's going to be launched to space at the end of 2024 or the beginning of 2025. Now, how do we get to this telescope? So, you see, I'm in my office, there are no telescopes lying around. So to achieve this, we built a consortium of partners. And the main partners that initiated the program are the Weizmann Institute of Science, where we sit, and the Israeli Space Agency together. And we recruited 3 major industries in Israel: the Israeli Aerospace Industries, IAI, which is the largest manufacturer of satellites in Israel and mostly works for defense. They manufacture the satellite. Oh, my light went out, sorry. So Weizmann is also very efficient in energy conservation. So, the telescope is built by ELOP, which is a division of Elbit, which is another very large defense contractor in Israel, who specializes in telescopes, again, mostly for defense, and now they are building a civilian things for science. And these very special UV sensitive sensors are produced by Tower Jazz, which is a huge factory for basically for chips and for sensors for cameras. One of the, if you have a cellular phone or a digital camera, large chances are that the sensor there is actually produced in Tower in Israel, in Migdal HaEmek. Because they only manufacture parts for other devices, you probably never heard of them, but they are very, very large manufacturer, and they make for us these very specific sensors. So these are three very large industries in Israel that contribute to the mission. And we have two international partners. One is a German institution called Helmholtz, or DESI, which is one of its subdivisions, which is the largest research institute producing sensors for particle detectors in Europe, and they are building the camera and the electronics that are surrounding these UV sensors. And the final partner, of course, not the least more important one, is NASA, that provides the launch of the satellite to orbit. So these are the main partners. There are a few smaller companies also involved. And finally, let me tell you a little bit about the science. So why are we doing all of that? Okay, it's interesting, and we have this big telescope, and we have all these partners, but of course, it all began from scientific questions. So there are many scientific questions. I would like to briefly discuss two of them. One that was mentioned in the video is what I call the question of the origin of the elements, right? So we are surrounded by materials around us, and we know they are composed of elements that are ordered in the periodic table of the elements. Many of us studied in school. And some elements are quite common. For example, iron is a very common metal and therefore also quite cheap. And some of them are very rare and precious, like let's say gold or uranium or other rare metals that are now actually quite often very sought after. And the question you can ask yourself is why is that? Why are some elements very common and some others are very rare? And how are all these elements actually formed in the universe? And even though this sounds like a very basic question, it's actually not answered. So we don't know the answer for all of that. There are many riddles about many of the elements which we don't understand exactly how they get to be there. In the Big Bang, where the universe started, the only two atoms produced in large quantities are atoms of hydrogen and helium. These are very light gases. And most of the material around us is not hydrogen or helium, right? Unless you have like a birthday party balloon or something with some helium in it. And most of the material surrounding you is not hydrogen and helium. And how these very light elements were synthesized into the much heavier elements and metals and components of our bodies and the planet around us, this is the main question we are studying. And the answer is that they were produced inside stars and in stellar explosions called supernovae, or in some mergers of very dense stars called neutron stars. And we have some examples for that, but to really understand this, we need to find these explosions very soon after they occur in order to be able to study the elements as they form. You can think about this as a furnace where new material is being minted, and UltraSAT being able to tell us, look, something just happened over there, allows us to immediately train our instruments there and look at the material as it is coming out of this furnace and understand what is coming out, which materials, how much of each material, which types of stellar explosions make which types of elements. So this is one question. There are many questions, but I will only give you two, right? If you want, can maybe talk later about other things. The second thing is another thing we are very interested in, which is the distribution of life or potential distribution of life in the universe. Right? We know there's life on Earth. We are very happy about this. But in recent years, we have discovered that there are around many stars that are similar to the sun. There are many planets that are, some of them are similar to the Earth. And the question is there life on some other planets in our galaxy, somewhere? And we don't know the answer to that. We know that there are planets where life may exist, but we don't know if they do exist. However, one of the dangers to life is the activity of the star. Some of you may have heard that even our sun, which is a very nice star, and we are, of course, the fact that we are here says that it's a star that is hospitable to life, from time to time has all kinds of activity that could be disturbing to us. For example, it could interfere with communications, it could be dangerous to astronauts that are in space and so on. And this is from the sun, which is a very relaxed star. Some other stars have much more violent activity, including very strong flares of UV radiation. And this UV radiation from a flaring star can really be disruptive to formation or persistence of life on a planet. For example, it can just wipe out the atmosphere or break down all the oxygen molecules and so on. And the frequency of such flares around stars is actually not measured because we cannot see them from the ground. So one of the things UltraSAT will measure is which stars have such flares, such big and violent flares, how often this happens. And this will tell us, among the many possible stars that might host life, which of them are really hospitable to life and which ones are not. So these are two questions, but there, as I said, there are many others.
Right. So so the origin of heavy elements and other elements, and then possibly the existence of life in exoplanets outside of our galaxy. So this is a big program at Weizmann's space program. In addition to UltraSAT, Weizmann is also building an observatory, land-based observatory of telescopes in the Negev desert to utilize its clear dark skies. So why is this project unique, and how does it complement the UltraSAT project?
Right. So you remember we discussed that it is very beneficial to observe a big patch of sky. And for a long time, this has been a problem also from the ground because of two things. First of all, telescopes and cameras are expensive. So if you just want to observe the entire sky, you have to build many of them, and this costs you a lot of money. But also, there is a trade-off. So if you build a larger telescope, it means that your field of view is smaller. This is the nature of optics. And you want big telescopes because you want a sensitive instrument that can collect a lot of light, but then your field of view gets smaller and smaller. And my colleague Eran Ofek, together with Sagi Ben-Ami, two people here at the department, actually find a solution to this problem, which is a combination of a scientific and economical problem, because you want to do science, but it also has to be affordable. And they have shown that recent advancement in off-the-shelf components allows you now to build very large array of small telescopes, which are, maybe this big, like as big as a small microwave oven, let's say, or something like that, which you can buy commercially from suppliers. And you can equip them with efficient cameras that you can also now buy commercially. And you can make an array of these relatively small telescopes and combine the data from these many, many small telescopes into one image, which is as if you had a much larger telescope, but for a price that you can afford. And the new observatory in the Negev is the first place we are going to actually use this technique. So the first array is actually being built right now. It has 48 small telescopes that together can act as one large telescope, much larger than any other telescope in Israel and comparable to large telescopes abroad, with a wide field of view and high sensitivity. And we just demonstrate this in tests we've done recently. And the Negev is a very nice place to build an observatory because it has about 300 cloudless nights per year, right? So most of the year there's really perfect weather for astronomy. And we built it in Neot Smadar, which is a very nice place that is also hospitable to astronomers. It's very dark. So this is the new technology observatory we're building. It's new. And we're hoping to have this first array active at the beginning of this year. And it will support also from the ground UltraSAT in space, because as you remember, UltraSAT will have this wide field of view and will observe in ultraviolet light from space. From the ground, we cannot observe ultraviolet light, but we can observe visible light, like the light that we see, and also infrared. And we will combine these additional measurements from the ground with the data from the satellite to understand all of these phenomena much better.
That's great. So it's amazing how Weizmann really has been on a roll in its involvement with space exploration in the last couple of years and moving forward. But it was just in the news and announced that Weizmann will be a partner in the giant Magellan telescope being built in Chile. What makes this telescope a game changer, and why is Weizmann taking part?
Yes. So, by the way, I don't know how many of you follow it, but in the US, you have a process called the Decadal Survey of Astronomy and Astrophysics, where the best minds in the US, under the National Academy for Science, meet up every 10 years and decide what is the top priority science projects in the US. And it's just been released 2 weeks ago that the Giant Magellan Telescope, which you just mentioned, is the top priority US project for ground-based astronomy, which we have just joined before it was announced. So we sort of predicted it. And what's so special about this telescope? This is a huge telescope and very, very expensive. So I described before how you can do with an array of small telescopes all kinds of things that are comparable to big telescopes. Well, one thing that you cannot do with a small telescope, and this giant telescope, which has an aperture, right? So it's effective collecting area of the main mirror is 25 meters. Okay, it's extremely large. One thing that a big telescope can do that smaller telescope cannot do is they have high spatial resolution. What I mean by that is that if you have two objects that are close to each other and you want to observe separately the light from the two of them, you need a large telescope in order to have this separation, because this separation is proportional to the aperture of the telescope. So even if you have many, many small telescopes, they will not be, the light will be mixed. You cannot set these apart. Why is this interesting? Remember the planets we were discussing, these other planets around other suns that you want to study and see whether there is life over there. So imagine that you are looking at our solar system, the Earth moving around the sun, but you're not looking from around here, but you're looking for a very distant star. The light from the sun and the light from the Earth will be blended together because the Earth is close to the sun and the sun shines much more light than the Earth, right? The Earth doesn't create any of its own light, it just reflects a little bit of sunlight. So if you want to study the Earth and answer, for example, the question, what sort of atmosphere the Earth has and what sort of elements are there, and maybe there are signatures of life in the atmosphere, you have to separate the little bit of light that comes from the Earth from the huge amount of light that comes from the sun. That requires high spatial resolution. So this big telescope will allow our scientists to use its huge mirror in order to study specific planets moving around suns, distant suns. So these are we call these exoplanets, right? They are planets outside of our solar system, very distant, and study them for signatures of life. And Sagi Ben-Ami, who's my colleague down the corridor here, is building actually a specific instrument. It's a spectrograph that allows you to look at biosignatures, so signatures of specific molecules in the atmosphere of these distant planets that can tell us whether there's life there or not. Now, we don't know. It's not, maybe the answer will be that there's no life there, but we will be able to look for life around in planets around other stars using this huge telescope. And very few institutions around the world will have access to these large telescopes in a way that the Weizmann now will have.
It seems like it's all these things coming together are really amazing. But I think the final question I want to ask before we open it up to the audience is, with the launch of UltraSAT, the observatory in the Negev, being with the Giant Magellan Telescope, and the Frontiers of the Universe initiative, why Weizmann and why now after all of these years?
So let's separate the two questions. So why Weizmann and why now? I will, with your permission, I will start with the second one. Why now? So why now has one major answer, and this is the technology is there. All of these things, UltraSAT, the giant telescopes, this large array of small telescopes, we couldn't have done them not even 10 years ago, and I know because I've been there. So these are just dreams coming true for us by new technology that has become available. And part of this technology is being developed and manufactured here at Weizmann, and part of it comes, of course, from the larger industry. But this has become now possible. Now, why Weizmann? So Weizmann is a special place in the sense that you heard from Roy that he doesn't have any strategy, right? So it's not like the Weizmann Institute decided 10 years ago, well, I want to do astrophysics. They hired some people, one of them was myself and of course other colleagues. And they let us do whatever it is that we want to do. And now all of this work has materialized. These things have been developing for a lot of years, for many years, at least a decade. And suddenly this achievement is at the tips of our fingers, right? So we can do that, right? We can look for life around other stars. We can understand how the elements around us were formed. And the management, the Weizmann management, true to its own principles, said, okay, this is what you need to do. this is what you should do. And so this is why we're doing that at Weizmann, and this is what we're doing that now. You cannot do it in any other institution in Israel. It doesn't have this scale of initiatives, and very few institutions in the world actually support this size and this scale of
Okay, well, thanks. That's great. So I want to open it up to some questions that we've received. And again, to remind everybody, if you'd like to ask Avishai a question, please just type it into the chat and we'll try to get to it. So the first question is, by the way, as no surprise, this is a very educated audience. So some of these questions I'm sure you'll enjoy. The first question is, what is the advantage of using near ultraviolet spectrum as opposed to visible, infrared, or microwave?
Right, excellent. So many of the events we are interested in are very hot. Now, for example, imagine a star exploding. So the temperature initially will be around 1 million degrees, and then it cools off and it's only 50,000 degrees. Anyway, it's extremely hot, and most of the emission, most of the radiation comes out in the ultraviolet. And if you just look at visible light or infrared, initially you just don't see anything. And even if you do measure using a very sensitive instrument, you might be able to measure maybe 1% of the entire radiation. So it's going to be difficult, and it will not tell you a lot of information about what's going on. Everything happens in the UV. Later on, when things cool down, it does move into the visible and infrared. And then, by the way, by then we will be there to observe it. But if you really want to see how things start, you have to be in the UV. And this is the reason, by the way, that none of this science has been tackled so far. So if you say, well, it's interesting to see a star explode, how many of them have we observed so far? The answer is one in all of our efforts over many decades, which was observed by chance by an instrument that was looking at one star exploding, that exploded, let's say, half a year ago. And then while it was looking there at the stars that exploded half a year ago, another star in the same galaxy exploded, just by chance. But this happened once in the last several decades. And so we have one example. We little bit know about what you're talking about, but UltraSAT will just do it every day, hundreds of events like that every year. So we can really understand this systematically.
Great.
Yes, so this is why we do.
Okay, the next question is it possible that the satellite might detect ultra heavy atoms with nuclei above the size as yet detected on Earth in the so-called island of stability, as predicted by Glenn Seaborg in the 20th century?
Right. So one of the targets we are looking at are mergers of neutron stars. So neutron stars are stars made almost entirely of neutrons, and some of them are in pairs, and some of them eventually merge and collide. Those of you who have followed the news, in 2017, there was the first time this was detected by gravitational wave detectors in the US. This was a huge event. And we also studied it here, both theoretically and observationally. And if you are thinking about how can if such an island of stability of extremely heavy elements exists, you can ask yourself, well, what technology can lead me to reach these very rare and extreme conditions? Well, merging two neutron stars is probably the way to go, because you have huge amount of mass at very high densities. And we know these things create all kinds of strange radioactive elements. I can't say that in the one event we studied, we have seen such things, but if we were to look for somewhere, this is where you have to look. And by the way, you need a combination. So UltraSAT can tell you where the thing happens, but to study it, you need a big telescope with a spectrograph, because new elements will have new spectroscopic signatures that we will have to use in order to differentiate them from regular elements that we see all the time. And so the combination, for example, of UltraSAT with a Giant Magellan Telescope, which is a very sensitive instrument on the ground with very high resolution spectroscopy, could do the trick. I'm not saying that we will be able to do it. If it exists, it is one of the most promising ways to attack this question.
That's a great question. Thanks for the answer for that. So when you detect a cosmic explosion, how long does it last? And how much time do you have to redirect your instruments to capture the events?
Right. So the explosion have several phases. So the first phase that happens is, when a star explodes, there's a shock wave traveling from the inside out. This shock wave is just, imagine you release a lot of energy at the center of something, and then it propagates out, and then it breaks from the surface. So this is the first stage. We call it the shock breakout. So suddenly there's a lot of energy coming from the surface of a star that until that time you didn't know it even exploded. And that phase is very quick, and it takes maybe tens of minutes. And this is something we have never seen before, and UltraSAT will be able to do because it will happen inside the field of view. So we will be able to see it from the first minute. Later on, this debris that used to be a star is expanding and cooling and emitting more light. And that can take between a few days to a few months and even years. And it gets dimmer and dimmer. You need more and more sensitive instruments. But UltraSAT will be very good at telling you when it happened, where it happened, and giving you information about the first phases that we have never seen before. How quickly you need to redirect your instruments? As soon as possible. So UltraSAT will give us the information in about 10 minutes. It will have a constant link to a ground station here in Israel. So the satellite will send down the images. We will know something has happened within minutes. Now, how soon you can direct your telescope depends on several things. So first of all, it has to be nighttime where your telescope is, right? Not necessarily, right? Right now you can observe in Israel, but you cannot observe in California. In a few hours, it will be the other way around. So you want your telescopes to be distributed in different locations across the globe, so it will always be nighttime somewhere. And in addition, there's the north and south hemisphere. So if something happens in the north, you cannot observe it from the south and so on. So we want instruments both in the north, for example, in Israel, and instrument in the south, for example, is one we are building right now in Chile. So if you have a network of telescopes, and we are actually I think we are the leading group right now in the world in doing that, we can get onto a supernova, onto a stellar explosion in an hour. And we are doing that right now using data we get from California, actually from Palomar Observatory. We find supernovae. We are using the same thing that you are enjoying now, right? So when it's nighttime in California, it's daytime in Israel. So for me to look for explosions in Israel does not require me to stay up at night, every night, which is very good. And so me and my students, we look at the data, we find new explosions, and then we trigger a follow-up observations usually from a telescope in Hawaii, the Gemini telescope, which gives us a little bit of extra time because Hawaii is further west from California, so the sun sets there a little bit later, so we get a little bit more time during the night. And our best record is about 1 hour to get on target. And we should be able to do better than that with it.
All right. I have a question about partnerships with other scientists, astrophysicists around the world. Do you work with any scientists here in the Bay Area, for example, at NASA Ames or the Caltech Nobel Prize winning team, Gravitational Wave team? And before you answer that, gravitational waves are really interesting. And I'm not sure that anybody knows about it. So maybe you'll explain a little bit about the hope and promise in detecting gravitational waves as well.
Right. So the answer, of course, is yes. I work with many of them, but let's talk about gravitational waves and then return to this question. So to understand gravitational waves, we have to go one step back and think about other types of waves, which we are all enjoying right now, which are electromagnetic waves. These are, for example, light that illuminates myself and you, and also radio waves or other types of electromagnetic radiation that allows information, for example, to propagate from me to you at the speed of light. So electromagnetic radiation is a change in the strength of electric and magnetic fields that propagates through space, right? So a light ray is actually the fact that the strength of magnetic and electric fields changes in space, the strength and direction of this radiation, or these fields changes in space and moves from place to place. The same thing can happen with another field, which is the gravitational field. And it's a prediction made by Einstein many years ago. And Einstein had this idea. He said, well, gravity creates a field. And if something was to perturb this field and create some sort of changes in the strength, and this perturbation will travel in space, it will create a wave, which he called gravitational wave. And he also calculated and showed it should propagate at the speed of light. And this prediction was made more than 100 years ago. And it took us about 100 years to build an instrument which was sensitive enough to detect gravitational waves. And this indeed happens. Now, what makes gravitational waves? Okay, you have to have something very heavy because, gravity is made by heavy things like the Earth or the sun. So if you take a very heavy star, let's say a neutron star, and you manage to somehow move it in a periodic way, you will change the field of gravity in a periodic way, and that will create a wave, and the wave will propagate and move to somewhere else. But how do you move a neutron star periodically? Well, use another neutron star. So if you have two neutron stars and they move around each other, then you see that you get a very heavy mass moving in a periodic way, and that creates a periodic signal that travels through space. And those are gravitational waves. And the nature of gravitational waves is that the strength of the wave is stronger if you have more and more massive objects that are closer and closer to each other. So we see the gravitational waves from neutron stars when they are about to merge together, to hit each other. So they are moving around and closer and closer and closer until they are almost merging, and then we get the strongest signal, and then they merge, probably make a black hole, and then the signal stops. So these are gravitational waves. They have been detected now many times, mostly from either binary black holes that move around each other, which are even heavier than neutron stars, or from binary neutron stars. And indeed, recently there was the Breakthrough Prize was awarded to a team of astronomers from the US, from Caltech, and from Berkeley, and from Texas, for their work on helping characterize the emission that comes from gravitational wave source. These are all people that we work with very closely: Mansi Kasliwal, Greg Hallinan at Caltech, Alessandra Corsi in Texas, and Raffaele Margutti at Berkeley. So as was mentioned before, I spent many years at Caltech, and we still have very close ties with that institute, but we also work, my ties with Berkeley go even further backward, because I worked with Alex Filipenko, who's a very famous astronomer at Berkeley. I worked with him as a student when I was a student in Israel, and he was very kind to, he was a powerful astronomer with excellent facilities provided by University of California, and the fact that I got a little bit of those of access to these resources was a very kind gesture from him, and helped me a lot as a young student here in Israel. And we still work together quite a bit. People at Berkeley, people at Caltech, and other institutions, of course, yes.
Very good. So here's a question that you may be able to answer partially, and I can fill in the rest if you're not comfortable answering. It's not an awkward question, but it's more of an institutional question rather than astrophysics question. It says, the question is, how does the Institute select among proposed research projects? How does the Institute encourage multidisciplinary study? And does the Institute receive financial benefit from its original intellectual property?
Sure. So I can answer all of those questions. I think one of my many hats that I wear, I'm also a board member of YEDA, which is our tech transfer company, and I've been doing that for many years, so I'm quite familiar with our IP issues. So this is not maybe broadly known, but the Weizmann Institute is by far the most successful institution in Israel in monetizing IP produced by scientists. With in this industry, you call a blockbuster drug a drug with sales above $1 billion. Weizmann has received royalties from 5 such drugs. Each one of them, one is very well known, the Copaxone that was mentioned. There are 4 other ones that are not well known. Each one of them is a blockbuster drug. So Weizmann is very good in producing IP and monetizing it, and has been doing that for a long time. It's, as I said, by far the most successful in Israel, and among the top 10 in the world, together with MIT and Stanford and the best ones that you are familiar with. We usually do not advertise it. We also do not hide it. It's not a secret, but it's not, as Roy explained, we are curiosity-driven institute. We did not come here to produce drugs or encryption codes or whatever. This is, by the way, one of the other things. I think all of us use an encryption protocol called RSA, which is used for bank transfer. And whenever you use HTTPS, this S means that your transaction is encrypted, typically by this RSA protocol. And RSA is the names of the 3 inventors, and the S stands for Adi Shamir, which is a Weizmann Institute professor. And there are many, many other things like that. So certainly we do patent the intellectual property produced by scientists, and the Institute has a very professional body that takes care of this in order to get the most revenue out of those inventions. and use them. It's a non-profit, right? So these revenues don't go anywhere. They just go to support more science and hopefully more inventions, right? And so this is about the IP. And by the way, this proves, in my opinion, that curiosity-driven science is actually the best, right? Because there are other institutions that have a lot of applied science and they do less well. So it means that I think eventually curiosity-driven science really gives you an edge in finding new technologies, not making known technologies a little bit better, but finding totally new ones. So that's about IP. Now about multidisciplinary, so as Roy said, we are really a borderless institution. And let me just give you one example that has to do with myself. So I teach astronomy. I teach a course in astronomy. And a few years ago, there came a student and said, I want to enlist to your course. And I said, sure, why not? And he said, well, the reason is that I'm a student in mathematics and I've never taken any physics courses at all. And in principle, isn't that a problem? So I said, we might be missing some materials that is known, needed for the course, but if you want to take I have no problem with you taking the course. And if you find it difficult, I can give you some advice about books you can look into or something like that. And the teaching committee will approve it. And they have. And the student came to the course. And during the course, by the way, he asked a very good question that I haven't talked about and eventually ended up as a patent we both issued on a new type of device. And then he said, well, astronomy is pretty nice. I want to become a student in the Faculty of Physics. So I went to the teaching committee and I said, well, this student wants to become a student of physics. And they said, okay, well, what physics courses he has taken? And I said, he hasn't taken any physics courses, never, including in high school. He never studied physics at all. Now, usually we are flexible, but this was really stretching it. So they said, well, what do we want to do? So maybe we should send him to Tel Aviv University and he can take some physics courses there and come back. And I said, no, this guy is really a genius. We are not going to send him to any other university. So what we agreed with the head of the teaching committee is that he's going to take the two very difficult core physics compulsory courses. And if he passes them in good grades, then we will assume that he knows all other physics that is needed and he will be accepted to the program. And I went to him and I said, okay, this is the decision. You have to take these courses. I suggest you take one course now and the other course next semester. And he said, no, I will take both of them together now. He said, you have never studied physics before. These are difficult courses. He said, no, it will be fine. Don't worry. There are some online courses from MIT. I already took some of them. It's going to be okay. I thought to myself, okay, let's see if it's going to be okay or not. It was okay. In one semester, he did his two courses, got excellent grades. The teaching committee said, okay, we'll get him. And he got a PhD in physics without having ever studied any physics anywhere. And now he's a faculty member in physics. And I was telling you the story to show that when we say we have no borders, we really mean it, right? So if somebody is exceptional and they can do it, then we don't insist on procedure, right? So yeah, in principle, you have to have all kinds of compulsory or some things in order to be accepted to physics. But if you can show that you really know this, it's fine. And it's the same way, I'm just giving you my example, but there are many, many other examples. There are faculty members in biology, energy again. That, physics faculty moving to biology, chemist moving into whatever you want, everything can happen. So this is about multidisciplinary, and students can work from one faculty, can work with another faculty member as their advisor. They can do it together. We can work with people from other faculties. Everything is possible. So this is about multidisciplinarity. And the first thing was,
that's okay. That's okay. That's good. I just wanted to just add to it that even among the researchers and scientists of Weizmann, it's very multidisciplinary because a lot of you live there on campus. And so you discuss when you drop your kids off, when you're playing tennis, when you go to eat, when you're walking your dogs. And these ad hoc conversations lead to some of the greatest collaborations on campus that wouldn't have ordinarily happened within the walls of the physics building or the chemistry building or the math building. Some of our best researchers in cancer are physicists. So we're getting a little short on time because I promised everybody by 12:15 or before that we'd be done. I just wanted to ask there's two more questions. One was I just want to go back to some Israeli space that just happened. I guess it was about 2 years ago, maybe less. The Bereshit mission that was launched to the moon,
Right.
which it wasn't successful in the end. It didn't achieve its mission. So how does Weizmann's space program relate to that effort? And were Weizmann scientists part of that Bereshit mission?
Yeah. So yes. So Bereshit did not start as a science-driven mission. We have to remember that. It was not a science mission. It was a mission to do all kinds of other things, to bring technology to the moon and bring Israel to space and all kinds of other things, but not science. And by the way, this is not how we work, right? We do scientific space missions, and the driver is science. Bereshit, it wasn't like that. However, since people asked for us to help, we said, fine, we will help. And we have helped. And Daniel Zeifman, who was then president of the Institute, and some of you may know him, was actually head of the directorate for that project. And we helped them in many things. But we asked for a small price, and which we said, in order for this to be really interesting and long-lasting effect, it has to have some scientific content. And this scientific content was a small experiment devised by my friend and colleague Oded Aronson from the planetary department, which was designed to measure the magnetic properties of the surface of the moon, which you can do even with a small device that he built and was installed on the mission. Of course, it didn't reach the surface of the moon in one piece, so we didn't get to do the experiment, but there was a Weizmann experiment on that mission. And I think the thing that UltraSAT brings that also had, and Bereshit demonstrated that, was what we call, and I'm sure you are all familiar with it, is what we call the Apollo effect, right? So when you do a space mission, it has such a huge appeal to young minds that this is one of the greatest way you have to attract young people to science, not necessarily to astrophysics, right? To science in general, including the medical sciences, engineering, whatever. And Bereshit had a sort of Apollo effect on kids in Israel, and UltraSAT will continue this. And we have a big project with the Davidson Institute here on campus to foster exactly that. So we are already doing stuff, including pilot projects in school as we speak. Well, okay, now it's nighttime here, so not as we speak, but we did that earlier today. Already starting to think and talk with teachers and high schools and elementary schools and even retirees who have grandchildren and all kinds of different communities in Israel in order to see how we can bring this excitement of the UltraSAT mission to them to continue this Apollo effect that Bereshit sort of started.
And so the last question is this UltraSAT satellite launch a one-off project, or are there future plans for other satellites after UltraSAT from the Weizmann?
Yeah, so excellent. Yeah. So it's a great question. So the answer is no, it's not a one-off, and we don't believe in one-off. I think in order for these things to really have an effect, they have to be part of a program. And talking to a US crowd, it's of course that because NASA is not a one-off thing, right? They have a space program that continues for decades and decades. But we believe that Israel should do this the same. I think we demonstrated with UltraSAT that you can do cutting edge, really break the frontiers of science with an affordable mission, which is definitely within reach of the Israeli state and Israeli institution like Weizmann. And we see no reason that there will be no second and third and fourth missions after UltraSAT. In fact, I think one of the big impacts we already see of UltraSAT is that the Israeli Space Agency, that up until now did not conduct any scientific missions, has itself grown and developed because of UltraSAT, and now is capable to do that, including working with NASA and working with the European Space Agency and working with scientists and with big industries. So all the infrastructure is there, and as soon as, actually, well, I'm saying as soon as, but actually I'm lying. I'm already thinking about the next space mission after UltraSAT. But I have to stop myself because first we have to get UltraSAT successfully into orbit. And then we will have more fun developing the next ones.
Absolutely. So one thing I always hear from Weizmann scientists is that going to work every day is like playing in the sandbox as an adult. You just get to do what you want. You have academic freedom, curiosity. You can follow your curiosity. And then actually now we're launching satellites into orbit around the Earth. So Thanks very much, Avishai, for joining us and sharing with the Emanu-El community. For those in the community, if we didn't get to your questions, I live here, I'm a member, I go to Temple. I should go more frequently, but I don't. But you can catch me, or if you talk to Ariana or anybody, you can reach out to me with any questions, and I can send those to Avishai or to Roe to answer those. In the meantime, if you ever do go to Israel, please give me a call because I'd love to just arrange a trip for you to visit one of the most beautiful places. It's park-like. It's almost 300 acres. There's still a few Jaffa oranges growing on campus, and so much science and fun goes on that campus. It's a delightful place to visit, only about 20 minutes, depending on traffic, from Tel Aviv. And you're always welcome to join us there. So thanks, everybody, for being part of this. Thanks, Ariana and Jordan and Alex at Emanu-El for putting this together, and Avishai and Roe in Israel. We look forward to our next IAC program coming up in the future. And Avishai, have a good night. We're just going to go to lunch now, everybody else. Take care.
Yes, thank you. Take care, everyone. Hope to see you soon here in Rehovot.
Yep. Bye.